The operating principle of a direct current, DC, motor is based on electromagnetic induction and the control of current direction. This principle allows electrical energy to be converted into mechanical energy, specifically rotational motion. The DC motor is designed to continuously adjust the direction of current in the rotor, enabling it to rotate in a consistent direction. Let's take a closer look at how a DC motor works. 1. Basic structure. A DC motor primarily consists of the stator, rotor, brushes, and commutator. Stator. The stator is the stationary part of the motor, containing strong permanent magnets or electromagnets that create a magnetic field. Rotor. The rotor is the rotating part inside the stator, with coils of wire wound around it, through which current flows. Brushes. The brushes connect the external power source to the commutator and are responsible for transmitting current to the rotor. Commutator. The commutator reverses the direction of the current in the rotor, ensuring that the motor continues to rotate in the same direction. 2. Operating principle. The operation of a DC motor involves the following steps. 1. Current supply. When current is supplied from an external source, it is transmitted to the rotor's coils through the brushes. 2. Electromagnetic force generation. When current flows through the rotor, it creates a magnetic field around the coils. This magnetic field interacts with the magnetic field created by the stator, generating a Lorentz force. The direction of the Lorentz force is perpendicular to both the current and the stator's magnetic field, and this force drives the rotor's rotation. 3. Rotation of the rotor. The commutator changes the direction of the current in the rotor depending on its position. This ensures that the direction of the force acting on the rotor remains constant, allowing the rotor to continue rotating in the same direction. 4. Continuous rotation. As the rotor rotates, the commutator maintains contact with the brushes, repeatedly reversing the current's direction. This process ensures that the rotor continues to rotate at a constant speed. 3. Control of the DC motor. The speed and direction of a DC motor can be easily controlled by adjusting the magnitude and direction of the current. Increasing the current increases the force and speed of the rotor, while reversing the current changes the rotation direction. This makes DC motors widely used in applications that require precise speed and position control. 4. Applications of DC motors. DC motors are used in various industrial and household devices due to their precise control capabilities. They are commonly found in robots, power tools, drones, car window mechanisms, and household appliances. Additionally, DC motors can be easily powered by batteries, making them suitable for portable devices and small applications. In summary, DC motors play a crucial role in various applications by converting electrical energy into rotational motion through the principles of electromagnetic induction and current direction control. The operating principle of an alternating current, AC, motor involves using alternating current, AC, to create a magnetic field, and through the interaction between this magnetic field and the rotor, rotational motion is generated. AC motors utilize the characteristic of a magnetic field that naturally changes with the periodic variation of the current. Due to their relatively simple structure and low maintenance requirements, AC motors are widely used in various fields, including industrial machinery and household appliances. Let's take a closer look at how an AC motor works. 1. Basic structure. An AC motor mainly consists of the stator and rotor. Stator. The stator is the stationary part of the motor, where coils are wound. When AC flows through these coils, a magnetic field that periodically changes with the AC cycle is generated. Rotor. The rotor is the part inside the stator that rotates, driven by the magnetic field generated by the stator. The rotor is usually designed as a short-circuited structure, often in the form of conductive bars, for example, squirrel cage design. 2. Operating principle. The operation of an AC motor involves the following steps. 1. AC current supply. When AC is supplied to the stator's coils, the current periodically changes direction over time. This changing current generates a periodically varying magnetic field within the stator. 2. Creation of a rotating magnetic field. Due to the spatial arrangement of the stator's coils, the magnetic field generated by the AC current has a rotating characteristic. This rotating magnetic field rotates around the rotor at a constant speed. 3. Induced current in the rotor. As the rotating magnetic field passes through the rotor, an electromagnetic induction occurs, generating a current in the conductive bars of the rotor. This induced current creates its own magnetic field within the rotor, which interacts with the rotating magnetic field generated by the stator, producing a rotational force on the rotor. 4. Rotation of the rotor. The rotor rotates in the same direction as the rotating magnetic field created by the stator. During this process, the rotor gradually accelerates and eventually reaches a speed close to that of the rotating magnetic field. This state is known as synchronization, where the rotor maintains a speed close to that of the stator's rotating magnetic field. 3. Types of AC motors. AC motors can be broadly classified into two types: induction motors and synchronous motors. Induction motor, the most commonly used type of AC motor. The rotor does not require a separate power supply, as it is driven by the current induced by the stator's rotating magnetic field. Induction motors are simple, robust, and widely used due to their low maintenance needs. A common example is the squirrel cage induction motor. Synchronous motor. In a synchronous motor, the rotor rotates at the exact same speed as the rotating magnetic field of the stator. The rotor of this motor rotates at a constant speed, directly synchronized with the frequency of the power supply. Synchronous motors are used where precise speed control is required. 4. Control and applications of AC motors. The speed of an AC motor is primarily determined by the frequency of the power supply. In typical induction motors, speed control can be challenging due to the fixed frequency of the power supply. However, recent developments in variable frequency drives, VFDs, have allowed for efficient control of AC motor speed and torque by adjusting the supply frequency. AC motors are widely used in industrial machinery, factory automation systems, HVAC systems, heating, ventilation, and air conditioning, and household appliances, washing machines, refrigerators, etc. Induction motors, in particular, are well suited for environments that require continuous use due to their durability and reliability. 5. Conclusion. AC motors are efficient and powerful machines that generate rotational motion by utilizing the periodic variation of current. Their operating principle is based on electromagnetic induction and the interaction of magnetic fields. Thanks to their simplicity and durability, AC motors play an essential role in modern industry. With advancements in AC motor technology and the integration of various control techniques, even more diverse applications are expected in the future.